HYLANTIC, the Atlantic network for renewable generation and supply of hydrogen to promote high energy efficiency. LNEG, innovative and safe hydrogen storage. Our society faces unprecedented challenges regarding the environment: climate change, pollution, deforestation, population growth, carbon emissions. Energy is one of the main areas that must be tackled in order to reduce the negative impact of human activity. Production from renewable sources, increased efficiency, and carbon neutrality are at the top of the list, but there are still some obstacles to overcome. Considering the targets of the European Green Deal to be achieved by 2050, zero pollution, affordable and secure energy, high-quality food, smarter transport, we conclude that the energy sector is a top priority and that hydrogen can play a key role in almost every goal. Currently, hydrogen is mostly produced by fossil fuels and used mainly in the chemical industry, but that might change within the next few years. It is expected to become a significant sustainable fuel that will contribute to the mitigation of climate change and the decarbonation of the energy system. In Portugal, the energy and climate targets for the 2030 horizon are very ambitious, and they are presented as opportunities for the economic and industrial development of the country in the energy transition. The opportunity for hydrogen in the next decade in the framework of investments is based on the definition of the recently approved National Strategy for Hydrogen that will support large-scale demonstration initiatives and research and innovation, integrating hydrogen in our options of decarbonization. The strategy is understood as facilitating the target compliance and objectives of the Portuguese Integrated National Energy and Climate Plan, the PNEC 2030, acting in the sectors where electrification is too expensive or not possible at all. Portugal presents very favorable and unique conditions to develop a hydrogen economy, including the existence of a modern natural gas infrastructure, very competitive renewable electricity production prices, and a strategic geographical location that facilitates exports. The projection of costs to produce green hydrogen using water electrolysis by the Hydrogen Council in 2020 considers average solar irradiation and aeolic conditions of member states in the EU. Portugal is in a privileged situation by exhibiting the lowest costs of production. Within the hydrogen projects presently in course at the Portuguese National Laboratory of Energy and Geology, LNEG, is the HYLANTIC Project. With partners located in the Atlantic area, HYLANTIC aims to establish an excellent transnational network to advance the R&D through the implementation of renewable hydrogen generation, safe storage, and efficient low-cost energy systems through innovative fuel cell design and H2 combustion engines. Environmentally friendly outputs will provide energy-efficient solutions to strategic sectors in the Atlantic region and benefit regional industries, generating positive socio-economic impact. HYLANTIC is developing different innovative routes for efficient and renewable hydrogen generation within the Atlantic area. LNEG contributes to the analysis of the state-of-the-art, looking at key issues on innovative engineering solutions for hydrogen storage in marine systems and coastal infrastructure. Recommendations to provide higher safety level at facilities of hydrogen generation, storage, delivery and use. LNEG is involved in several working packages in the context of innovative and safe hydrogen storage.
We have addressed it not only in the bottlenecks of the technologies, but also the critical issues, because there is a competition with fresh water to be used in these processes, and the power input, which represent a big chunk of the cost of the hydrogen produced, when, for example, it is electricity. So we have hydrogen production powered by renewables using pure water, powered by light using residual waters, and using no power at all because the reaction is spontaneous from a mixture of water and chemicals, where we develop the catalyst and the prototype reactors together with the management systems in order to advance toward applications in the maritime sector. In another process of hydrogen production, we use residual waters as a feedstock, integrating the hydrogen production with effluent remediation and valorization. In this case, the process of hydrogen production is powered by light. We produce photosensitive catalyst materials, and in this case are ternary new systems that substitute novel critical materials for transition metals, looking at increasing efficiency of these catalysts. We have managed to have very high rates of production of hydrogen and durability of the catalyst, extending also the irradiation times. The objective is also to enhance visible light utilization in order to use outdoor stations that capture visible light directly from the sun as reactors.
LNEG is in charge of developing the catalyst for the hydrogen production by a hydrolysis reaction, a laboratory reactor prototype, a monitoring and control management system. Most of the available research data on hydrogen production focuses on the search for catalysts, their characterization and catalytic activity, with experiments generally performed under atmospheric conditions.
We use water to produce hydrogen mixed with chemicals, in this case chemical hydrides, particularly sodium borohydride. And in this process, we use a hydrolysis, which doesn't need any power input as such, since the reaction is spontaneous and is exothermic.
Sodium borohydride is one of the most studied chemical hydrides, owing to its combined advantage of high hydrogen capacity, good stability in alkaline solutions, easy control of the hydrogen generation rate, friendly operation, and an environmentally benign hydrolysis production sodium borate. Hydrolysis of sodium borohydride can be easily accelerated by the simple addition of a metal catalyst. Half of the hydrogen comes from the water, giving sodium borohydride a relatively high theoretical hydrogen storage capacity of 10.8 in weight.
We have used an integrated approach of high efficiency and durable catalysts that have been produced by us. We have studied the reaction kinetics and have assessed issues of solubility, of water management, stability, for example, the effect of pressure also on the reaction rate, and other issues which are important, like starting the reaction at low temperatures, are near freezing temperatures.
But hydrogen generation by hydrolysis of sodium borohydride is not without problems. Heterogeneous catalysts can be added to reduce the activation energy and accelerate the generation of hydrogen. In the past 15 years, different catalyst systems have been reported for sodium borohydride hydrolysis, most of them powder-based and containing ruthenium, nickel, and cobalt, some even platinum. However, noble metals are scarce and expensive, so the use of catalyst systems based on the cheaper transition metals is highly desirable. Specifically, cobalt and nickel have been the most employed to date due to their low cost and abundance compared to noble metals. While searching for an efficient catalyst for the hydrolysis of sodium borohydride, LNEG opted for a supported catalyst on a metal foam rather than a powder-based one. The choice is due to high porosity, large specific surface area, satisfactory electrical and thermal conductivity, and mechanical stability.
We have also been involved in reactor design, correlating the performance of very small reactors that we started from with very small volumes of 5 milliliters to large prototype reactors. This is a complex task and also integrates heat transfer.
The prototype laboratory batch sodium borohydride reactor, made of stainless steel, has an internal multi-tubular structure that allows efficient heat transfer and can work safely up to 60 bar. The total of its internal reaction and storage volume is 21 liters. After 50 minutes reaction time, the total hydrogen produced was approximately 503 liters, reaching an internal pressure of 30 bar. The maximum production rate achieved was about 15 liters per minute. As stated, the reaction is exothermic, and the heat produced is extracted using water as a thermal fluid that runs in a jacket between tubes and the reactor shell in order to control the temperature-dependent reaction rate. The batch reactor system also includes a storage vessel for the produced hydrogen and external containers for the sodium borohydride solution and for the reaction's final residues that will be extracted from the reactor. In order to assure safe and optimal reaction conditions, the system integrates a custom-specific electronic monitoring and controlling system, allowing for the real-time control of several actuators and data acquisition during the hydrogen generation and storage process. The objective is to achieve an automatic on-demand control of the batch reactor to provide a quasi-continuous production and storage of hydrogen to fulfill the energy requirements intended to feed a fuel cell, according to the application. This electronic monitoring and controlling system, Hydrogen Management System (H2MS), was designed from scratch and has a modular hardware architecture, allowing a flexible and expandable hardware configuration. The H2MS system's customized hardware and firmware can be optimized and redesigned for different types of reactors and applications, allowing a final lower cost when compared to other off-the-shelf acquisition and control systems. The system's architecture allows the data acquisition from several types of sensors related to the most significant process variables like temperature, pressure, pH, hydrogen flow rate, etc. Due to the global reactor structure, several electrovalves and switching actuators are fundamental for the automatic or quasi-continuous operation of the system, so this management system can also drive different types of actuators. The design of the H2MS first prototype was completed with the assembled system circuit boards interconnected using a standard rack mounting panel that also includes the power supply modules. The H2MS system includes a local low-cost single-board microcomputer running Windows 10 environment using a touch-sensitive monitor for data display and user interaction. The high-level software application for reactors control and user interaction is under development, giving the possibility of real-time acquired data reactor status to be displayed in a synoptic dashboard. In the future, it will also be possible to access remotely the H2MS unit for data collection and control interaction. The integration of the H2MS system with the global sodium borohydride hydrogen reactor allows a more elaborate model characterization and operational optimization of the global batch chemical process. This is a key aspect to the development of new control models for optimized reactors' on-demand hydrogen production. The supported catalyst, synthesized, characterized and tested at LNEG, was shared with the FEUP, the Faculty of Engineering of the University of Porto, and with industrial partner A Silva Matos Company for further independent testing. Partner A Silva Matos has built an industrial reactor integrated in a system, with additional storage to be tested using LNEG's produced catalyst.
It was a very big challenge because the first reactor was built for 1 liter capacity, so the scale-up was very important. The aim of the project was to build a reactor. It has 120 liters capacity with a design pressure of 80 bar and the temperature design of 100 degrees Celsius. It was very important the use of the catalytic from LNEG, the sodium borohydride, to improve immensely the potential of the technology. I'm very happy with the results of this project. Now it's possible to use this technology in maritime or distant places to produce energy whenever any other solution is not possible.
This technology can be promising for the maritime industry, although applications and possibilities for onboard applications are still uncommon, presenting the use of sodium borohydride as an energy carrier with many potential advantages, such as a harmless, emissions-free, safe, and recyclable fuel. From the point of cost reduction in synthesis and post-usage of sodium borohydride, its regeneration from the byproduct of hydrolysis, sodium borate is in great need for the recycling of this hydrogen supply system. The HYLANTIC Project is approaching this issue with the collaboration of the University of Porto.
The concept relies on the production of hydrogen on demand in situ from a chemical reaction. We produce hydrogen using the hydrolysis of sodium borohydride. One of the main challenges of this concept is to be able to regenerate the sodium borohydride from the reaction products. At University of Porto, we discovered that using optimal concentrations of some specific additives, we're able to have a profound change in the structure of the borate. And let's say that we obtain zinc chalconate, which is a dehydrated form of borax, which is already ready to the inverse process, the regeneration process. So these groundbreaking results will bring down tremendously the costs of the regeneration process.
I consider that strengthening the research and development base in Portugal is a priority in the next decade to support demonstration at large scale and also emerging hydrogen technologies in the framework of the energy transition and our decarbonizing options and targets for the different sectors of the economy.
The concepts of the sodium borohydride system have a high potential for the maritime industry, for which this technology offers some advantages. Most important is the fact that vessels are surrounded by water, which can be used for the hydrolysis of sodium borohydride. At the current state of technology, much research still needs to be done to prove the concepts and make sure the systems can be implemented safely on this scale. The use of hydrogen as a fuel in boats has been demonstrated by the Energy Observer, launched in 2017 and considered a floating laboratory. The ship tests the efficiency of a full production value chain that relies on the coupling of renewable energies producing green hydrogen from seawater electrolysis and converting the hydrogen into energy in a fuel cell. A 11-metre hydrogen-powered ferry was built in Bristol, UK in 2011. It carries 12 passengers and 2 crew members and is operated by Auriga Energy, one of the HYLANTIC partners.
We've made the UK's first hydrogen-powered ferry, fuel cell-powered ferry with our fuel cells on board. What the hydrogen provides is a zero-emissions solution to all of our energy needs, particularly where we're replacing the internal combustion engine.
They have integrated 4 air-cooled hydrogen PEM fuel cells that provide up to 12 kilowatt of steady-state continuous power at 48 volts.
The HYLANTIC project brings together all of the different angles of the hydrogen economy, and I think we have achieved some great things so far. The hydride systems that are being developed in Portugal by the University of Porto and the LNEG will solve a huge problem within the use of hydrogen in transport in particular.
Sustainability targets for the transport sector are not limited to road transport. Shipping is an industry which is responsible for 2 to 3% of all CO2 and greenhouse gas emissions worldwide, according to data from the International Maritime Organization. Their strategy envisages a radical reduction of CO2 emissions of international shipping, 40% by 2030, and pursuing efforts towards 70% by 2050, compared to values of 2008. In achieving these targets, it is thought that hydrogen and hydrogen-based fuels have great potential to meet important operational requirements such as range and refueling time, as do conventional fuels.
Hydrogen is called to contribute not only limiting the carbon emissions, which obviously are related to climate change and to air quality issues, but also in the security of supply. The hydrogen storage capability and the association with the realization of the full potential of renewable energies will also contribute to the ambitious sustainability targets in the transport sector, and this includes shipping.
As the private sector starts to test technologies and even roll out new products, public awareness of hydrogen-related energy solutions is rising. The HYLANTIC Project has the ambition to actively contribute for a wider acceptance of hydrogen as a fuel, engaging in an intensive dissemination program that maximizes the impact of the obtained results. Alongside governments and research institutions, it seems that a truly global hydrogen ecosystem might become a reality.